The constellation Cepheus, named after the mythical king of Ethiopia, claims 57 visible stars, including Delta Cephei, a variable star that is the prototype for Cepheid variables. By a quirk of nature, Cepheids keep time like a metronome. The bigger and brighter the Cepheid, the slower it will pulsate.
So what you do is find a Cepheid variable, measure its pulsation period, it might be 10 days or 60 days, and then you've got a standard candle. You can determine how far away that star is.
A standard candle is a basis of comparison, a star of known luminosity and distance that we can compare similar stars against.
You know, a light bulb gives off the amount of light it gives off, a certain amount of watts. But that light is going to look a lot brighter if you're right up close to that light bulb than if you are 10 feet away. And so the luminosity of the star doesn't change. You know, that is what it is. But apparent magnitude, you know, depends on where you are, how far away you are, whether you're right up close to something or you're seeing it from the other side of the street.
If a Cepheid doesn't appear that bright, then it must be far away. Astronomers can calculate how far it is based on how dim it appears.
Looking at my Cepheid variable and plotting the light curve, how long it takes to go from brightness to dim to back to brightness again, tells me what the intrinsic brightness of that star is. So I can calculate distance to variable stars by observing the period of their variation.
That's how Edwin Hubble was able to determine that Andromeda was 2 million light-years outside our galaxy. But Cepheid variables have their limits. To measure distances far beyond Andromeda, astronomers rely on supernovas.
It turns out that supernovae can also be categorized as standard candles. Type 1a supernovae are all the same throughout the universe. We know how to calibrate them. And that's how we determine the distances out to the Big Bang and the very edges of the universe.
Peering into the Big Bang, scientists can nearly see the beginning of time. 300,000 years after the Big Bang. Even our most familiar constellations have a lot to teach us about the cosmos. Orion, which is Greek for hunter, has 77 visible stars. Alnidak, Alnilam, and Mintaka make up the 3 stars in Orion's belt. In modern times, astronomers have hunted Orion, finding a variety of astonishing objects.
When I see Orion, I also see the life and death of stars. Just below the belt, there's a little smudge called the Orion Nebula, and that's a nursery for baby stars, and you can actually see that with the naked eye.
Orion has also bagged a pair of stellar gems.
If you look at the upper left-hand shoulder of Orion, you see the red giant Betelgeuse, and if you immediately look right down to the lower right star, the star that's sort of his leg, you'll see the blue supergiant Rigel.
Betelgeuse, as a red supergiant, is a star in its death throes.
A red supergiant is a star that is actually quite a bit cooler than our sun, but much, much larger.
Betelgeuse is 14 times more massive than our sun. When it runs out of nuclear fuel, Betelgeuse will become unstable and implode in a colossal supernova. It can detonate at any time.
And when it explodes, it will light up the entire night sky, and it will even be visible during daytime. And maybe it's already blown up. It's 427 light years from Earth, which means that perhaps it has already exploded, but light hasn't had time to reach us yet.
The supernova will draw more attention to a sky that's been captivating us for thousands of years. The ancient Egyptians consulted the heavens to tell them when to plant and when to harvest. Every star possessed a sacred meaning. They called Sirius in the constellation Canis Major the star of Isis. Sirius's appearance before dawn during the summer solstice forecasted the annual rise of the Nile River. Other constellations, like Orion, might have had a certain architectural significance.
Egyptologists have often asked the question, why did the ancient Egyptians build 3 great pyramids that are slightly misaligned? Did they have bad ruler sticks thousands of years ago? The 3 pyramids seem to be aligned to the 3 constellation stars of Orion.
What does this alignment mean? Was it a coincidence, or were the pyramids intentionally engineered this way? The pyramids of Giza seduce us with archaeological mystery and historical intrigue. Some scientists think the pyramids have a certain astronomical importance.
It has been claimed that the layout of the 3 major pyramids on the Giza Plateau, including the Great Pyramid, are set on the ground to mimic the 3 stars in Orion's belt.
It's one of my favorite connections between events on Earth and events in the sky.
But the ancient Egyptians didn't see a hunter in Orion like we do. They saw Osiris, god of rebirth. Some speculate that air shafts within the Great Pyramids were specifically designed to catapult the souls of pharaohs to the heavens.
In those pyramids, we have 2 different shafts, and those shafts, one points north, one points south.
The south shaft points toward Orion.
So the soul of the pharaoh would be launched through that shaft in order to be connected to Osiris, Orion, and be resurrected again, enjoying eternal life.
But others are a bit more skeptical.
In order to make it match correctly, you have to flip it upside down on the ground or in the sky. That the Egyptians did place an importance on north and on south in the pyramid. And it doesn't make any sense to say, well, yes, they lined the stars up right, but then when it came to mapping on the ground, it was perfectly okay to flip everything around and make it upside down.
The north shaft points toward one specific star.
The one pointing north points to the pole star at the time, 2,000 years before Christ, 2000 BC, 3000 BC, and that pole star was Thuban.
Thuban is located in the constellation Draco, or the Dragon. Draco has 79 visible stars. Thuban has been replaced by our generation's pole star, Polaris. Polaris illuminates the Arctic, governing our sky as a beacon over the North Pole. Lying in the constellation Ursa Minor, it's 2,500 times brighter than the Sun. Outshining its companion stars, Polaris A, B, and B. Although it's ruled the heavens as our North Star for as long as we can remember, its reign won't last forever. As Earth orbits the Sun, it teeters back and forth. This wobbling is called precession. If Earth was a perfect sphere, it wouldn't precess. But the gravitational pulls of the Moon and Sun tug at the bulging equator, upsetting Earth's spin.
Now the Earth is like a gyroscope or a spinning top. Notice that if I spin this very rapidly and then I move the axis, it points in the same direction. This is the Earth pointing toward Polaris, that as the Earth goes around the Sun, it always points in the same direction. However, precession is caused by gravitational interference, so the Earth begins to wobble.
As Earth wobbles, its axis draws a circle in the sky. It takes 26,000 years to make one complete circle.